Hello, dear listeners. Welcome to Semaphore Uncut, a podcast for developers about building great products. In this new episode, Darko, our podcast host, welcomes software developer Bart de Water. Bart shares his expertise on the principles and strategies for creating reliable systems that can withstand potential and even unexpected failures. I hope you enjoy this new episode. Now let's dive in.
Hello and welcome to Semaphore Uncut, a podcast for developers about building great products. Today, I'm very excited to welcome Bart de Water.
Thank you for having me, Darko.
Can you please just go ahead and introduce yourself?
After I graduated from university in the Netherlands, I worked for a Dutch startup building single sign-on systems for governments. Then I moved to Montreal to work for Shopify. I did that for nearly 6 years. And then recently I joined a startup called Thatch.
You do have a focus for building resilient systems, and that's something that you have been doing for quite a while now. Can you give us an intro how you got into that and how it in a way became your focus point?
So at this startup, I think I had about maybe 6 to 12 months of working experience at the time. We were working on building a single sign-on system for the UK government called GovUK Verify. And when we launched in beta, like our systems and a couple of other APIs that we had to talk to were used for the first time. And all these, I believe it was farmers, all signed up for our service. And our service was fine, but this backend service that we had to talk to that we didn't own didn't handle the load well, and therefore also took us down. So what happened was we had a pretty vanilla Puma and Sidekick setup, if I remember correctly. Ruby's default HTTP timeout is 60 seconds. So these 5 or 10 threads were just all, waiting for 60 seconds to time out because of this service being down, which then led to also delayed jobs for sending email confirmation links or SMS messages with two-factor authentication codes. So people were complaining that they couldn't log in, they couldn't complete their registration, even though our system was fine. It effectively was down because of this other system being down. And that kind of started my fascination about okay, so, lower timeouts are better. And if you know that something is down, you might as well just stop trying for a little while, which is the circuit breaker pattern.
At Semaphore, we're all about helping startups and growing businesses achieve their goals. We're introducing the Startup and Scale-Up plans, which come with a per-seat fee, ensuring that we continue providing the additional value that our users expect. These plans come packed with several new features that were previously only available on our Enterprise plan, such as new machines with faster CPUs and double the RAM and disk space, self-hosted agents for easy auto-scaling and complete control, metrics and insights for improved build performance over time, streamlined releases with powerful deployment controls, and much more. Head over to semaphorecI.com/pricing for more information, and happy building.
If you would be talking to a young engineer joining either Shopify or Semaphore and building the system, in which order would you guide that person what they should be focusing on, not to shoot themselves in the foot and bring their system down and other systems down?
I would start with just every time you make a call that hits an external system in some kind of way, and that includes your own database, make sure there is a timeout that you've set, because depending on the system that you're calling, there might not be a timeout. Same thing for HTTP calls or calling your redis or anything else. Every time you make a call to an external system, think what the timeout is. Make sure there is one that is reasonably low. That is one of the easiest starting points. And I think that's also, you can generalize that to thinking through failure modes. Unless you've kind of already had the production experience where, you've been on call, you've been responsible for fixing a system at 3 a.m. in the night. You've learned that the hard way. So every time I see code coming by now, one of the first things that I think about in a pull request is okay, how's this going to fail? And have you account for these failure modes in some sort of way?
There is a great book that kind of also starts with timeouts by Michael Newgard. I think it's called Release It, or something like that. The story is similar to yours. It was like aeroplane system where, again, some default timeout in Java, there was no timeout actually. So it waited forever, which is much worse than waited, default 60 seconds in a Ruby.
And timeouts can also sneak up on you in unexpected ways. There's this blog called Accidentally Quadratic, I think it's called, about regular expressions that can take way longer to process process because of accidental quadratic complexity. And recently, Ruby got a timeout for parsing regular expressions as well, so that, a runaway regex doesn't take down your system or tie up resources too much either. So yeah, even internally in your programming language, there might be something like a foot gun waiting for you to stumble upon.
CI space, you have agents running around, and eventually they need to pass the logs back, they need to pass the status of the job back, and all of that. Something can happen in the middle. And then, for us, there were like two questions. One is, okay, the configuration of timeout, obviously. Then the question is, for how long should we wait to get system back in shape?
Yeah, so both at Thatch and at Shopify, I'm working in the payments related space. And a pretty common pattern there is for the APIs that you talk to your bank or your other financial partner, is that you can include an item potency key. So this is typically a randomly generated string. Every time you retry the same request, let's say you want to tell the bank that yes, for this incoming card authorization that one of our users at Thatch is, swiping their card at a pharmacy, is that, we want to authorize this. And if for some reason, like you said, networks are inherently unreliable, sometimes there's just a blip and it times out for no good reason, you want to try that again. You don't want to double authorize, because then the user's out of their money twice. So this way, this item potency key is basically this string that says hey, this uniquely identifies my intent to do this action. So please only do it once. If you see the same item potency key again, then just echo me back the first response that got lost somewhere in the internet, but don't double charge the card.
If you would retry something for a couple of times, what would be your rule of thumb?
It's really context specific. There are cases where you can only do one retry. Again, if you're like what we're building right now is that we're responding in real time to card authorizations. That comes with some real time requirements too. We cannot retry over a long period of time because the card networks tell us we have to give back a response in 2 seconds. So that's it. But let's say you're doing a background job to backfill some data from your upstream provider, then typically an exponential backoff, where it's okay, we retry after 1 second, then after 3 seconds, then after 5, you can go through the Fibonacci sequence to make sure that you're not hammering that other system unnecessarily, and you back off the more you need to retry. And then, you could cap the end of that retry interval at maybe a minute or maybe even 5 minutes. And that's totally fine too, because you don't care about how fast it's done, just more that it eventually gets done.
I can add an example where we went to a bit more extreme when it comes to I don't know what's the state of the system right now, but I remember back in the days, we initially started as a monolithic Rails application and all of that. But of course, the runners were spread around, different data centers and all of that, running CI jobs. And in those situations, we wanted to have a back of factors, and we waited up to 30 minutes. It's much better, even if a bit of delay, to recover the state of that job. And, the state machine gets, job progresses really from running to finished. And, so we salvage that data.
I'm curious, how do you deal with impatient developers who then just, force push a new commit to trigger another job?
Well, what I was giving as an example was maybe 5+ years ago when we have a monolithic application. We switched from being that monolithic application to being microservice oriented. So we have now a dedicated service whose sole responsibility is to receive the requests or process the jobs and so on. So I think that our interface generally is now much communicative, and it's not that we really have that pattern.
Yeah, because I think one of the most powerful things that developers can learn about after they've, gone about and lowered their timeouts a little bit more is then starting to understand queuing theory a little bit better. Because queues are everywhere. It could be, in Semaphore's case, I imagine that, you have a queue of jobs that all need to be worked on. But if I push commit A, and then I'm impatient and I push commit B with just an added new line to kick off a new job because my first one is taking too long, you want to preserve your resources as well. So will you cancel the job for commit A, or is there some sort of other back pressure mechanism to make sure that a trigger-happy, impatient developer like myself doesn't take down your system by just pushing a ton of jobs in your direction.
Yeah, queues are absolutely everywhere. Again, most of my horror stories are from the time when I did, hands-on, development, which I'm fortunately for the team or unfortunately not doing anymore. Yeah, I remember with just, you mentioned Puma at some point, I think as a Ruby server. And we also used Passenger, I think it's of Dutch origins, as far as I know. Yeah, queues there there is a queue, I think, of in Passenger of default, like 100 requests that are going to be queued. And that queue is what most developers, or maybe some never discover, and some discover, a couple of years in their career, that there is that queue there. And, that's one of the queues that you have to deal with.
Like there's a theorem out there for the people unfamiliar called Little's Law that describes the relationship between queuing and the amount of customers or work entering the system. So it's very intuitive to say that let's say you're in a supermarket and you're checking out and the cashier is taking 10 seconds to process your groceries. That is of course going to take a lot longer to process the queue for that cashier than if it were to take 5 seconds. But these properties of how long is the queue? When is it my turn? How long does it take to process an individual piece of work? A very simple formula that is super broadly applicable to all kinds of things. Whether you're, say, in Disney, waiting for your favorite roller coaster, or in a grocery store, or at a festival waiting for the toilet so you can get back to listening to your favorite DJ. It's everywhere. And the same thing goes for building software systems. To get back to that example that early in my career, where because of the queue latency was so high, by the time our background job system actually sent that message with a two-factor authentication code, that two-factor authentication code was already expired because it was also built in such a way that it first generated the code and then enqueued it for sending. If we would have built it in a different way, that it would, generate the code at the time of running the job, at least, yes, the codes would still come in delayed and our users would be annoyed, but at least they would have gotten a usable code.
Yeah. Now I cannot speak specifically, but I know that our platform team uses the same or a very similar type of formula, which is based on the arrival rate, and that's how we scale the cluster.
Yeah, so that is, I feel that, when people start thinking about monitoring their systems, I find that, unless you've learned all these things through practice, or you would have read Michael Nygaard's book before you were paged at 3 a.m., is that they typically, one of the logical things is we should keep keep tabs on how much requests or jobs per second or per minute we're processing, the arrival rate. But the latency oftentimes gets forgotten, or maybe at least, the latency on, say, the controller. You don't want to wait 5 seconds for your page to render. But then the latency for the background job system, I find, is often overlooked, while it is just as important. Because once that queue starts backing up, things start to fall over and you're still down.
Microservices architecture is all the rage these days. But do you know what it really means and how to implement it to empower your teams to make the best decision for the problem at hand? On the Semaphore blog, you can learn about microservices and how to take advantage of features like test reports, monorepo, and Docker support to build, test, and deploy your microservice application at scale. Head over to semaphoreCI.com/blog for more information. And happy reading!
For people that are, just starting and building their apps, what would be your 101 system reliability dashboard for a typical web commerce application, people starting out?
If the queue is long enough, you're effectively down. Like that example from those two-factor authentication codes. Just drop the work. The only way to eventually get this queue back into control is to either fix the thing that makes it slow, make your cashier, so to say, process these orders faster. But at some point, you also might have to say that, hey, we're not letting new people go into the store right now because the line for the cashier is already 30 minutes long.
There is one concept that we mentioned a couple of times, but we haven't properly introduced. So I would like you to ask if you can introduce, circuit breakers and idea around them and some of your experiences.
For the people who are not familiar with it, Google has published a virtual book about their site reliability engineering practices. That lists what they call the 4 golden signals. The first one is latency. So again, how long does it take to process a bit of work, whether it's a controller request or a background job or anything else. Also distinguish there between successes and failures. You install a circuit breaker and you say that hey, this API is down. You immediately start failing because, the circuit breaker in your house, it's open, so there's no connection happening. So that can skew your metrics if you don't make that distinction. It's then very normal to see that your failure latency is super low, like in the single milliseconds. Then the traffic or the arrival rate, that's just, how much stuff is entering our queues. And also the rate of errors. Are we just seeing the occasional error, or are we seeing half of every unit of work erroring out for whatever reason? And in payments, there's a distinction between, say, actual errors, like an HTTP 500 from your API that you're talking to, but a declined card because you have insufficient funds. Well, yeah, that's a failure, but it's expected, right? It's not an error. I'm talking about unexpected errors here. And then finally, the saturation. So this is sort of like a percentage-wise or relative load that your system is under. Could be memory used, CPU usage, maybe the amount of threads actually doing work relative to the total amount of threads available to do work. But this can also provide can highlight some misconfiguration. You might have, say, 100 available threads, but Ruby, due to its global interpreter lock, cannot effectively utilize 100 threads. So you might still see that the latency goes up, even though there are still, say, 80 threads available. Once you've lowered your timeouts, you'll notice that, once you're, the resource that you're talking to, whether it's your database or an API, once it is down, it tends to stay down for a while. It doesn't go down for just 5 seconds. It's probably down for minutes and hopefully not much longer. So while you are still, instead of waiting 60 seconds, you're waiting 5 seconds, that is still 5 seconds wasted. Since you can reasonably expect that, the next 10 calls are also going to time out, your system still could be doing something else. So after your timeouts are lowered as step 1, then my recommendation would be for step 2 is to figure out whether your web framework or programming language has a circuit breaker that once you've triggered an X amount of errors, that it short circuits the next attempt for a certain period of time. So let's say I am trying to move money with my bank API, and I've retried, the request, and I have 3 separate requests all failing within a window of say 30 seconds. Then I'm going to mark this circuit as open. And then the next API calls, they immediately just, they return early. They don't even try to make that call and again, wait for another 5 seconds. So that, that the background job is re-enqueued to be retried in a certain amount of time. So that frees up my capacity to do other things like sending 2-factor authentication codes.
From experience, I would add here that we had a number of situations where we restored the system, it went back up, and then down again because it was flooded by all those retries.
Yeah, it's called the thundering herd problem. And this is why when we talked earlier about retrying but backing off exponentially, that often there's also a random little bit of jitter added to that timeout, so that not 1,000 jobs are re-enqueued to come back in 5 minutes, because then 5 minutes later, you're going to take that other API down again because you're sending as much of these requests as you can at the same time. And one interesting thing from my own experience as well with circuit breakers is that when dealing with payments, Shopify's circuit breaker implementation called Semian recommends that you key the circuit breaker off of the API endpoint. And that works great for a lot of times. But the interesting thing about payments is that it's global, right? So you use this single endpoint to do payments worldwide. And what if your payment gateway, because they of course also talk to various backends, depending on the geography, the card network, etc. So one interesting failure mode that we had once is that payments went down in one country, but the error rate was sufficiently high that it triggered that it opened the circuit for that one particular endpoint. So we started short-circuiting payment calls for merchants in other countries that should have just succeeded. So that's when we added an optimization there, is that, we concatenated the merchant country to the API endpoint. So effectively, we had a per country circuit breaker, so that the next time there was an outage that was confined to a single country's payment network, that did not take down our global our global payment processing. It was really just localized to where the errors were actually happening and where that circuit breaker should only apply. But again, this was one of these things that, we've had in place for years. It worked fine up until we had an outage, and I was like, hey, actually, this doesn't make sense. And these are the more interesting failure modes to get in once you have your basics covered. And that's when your process becomes more important. It's like, how do you respond to these things?
I'm curious to know, do you have maybe a single place where you could follow all the circuit breakers? Or it was like per the service or domain? Or
at that time, no. Like what kind of led to the realization that we were circuit breaking sort of too broadly was that our financial partners were like, hey, payments were down in this country, and you should have, but globally it was not affected. And I was like, well, if I just look at my ratio of successes and failures, I saw that you seem to be globally down. Like, what's going on? They're like, well, they were confused by what do you mean we were globally down? We were not. And that's when you start kind of collaborating. They sent over their data, we looked at ours, and then it was like, oh, wait a second, we know what's going on here. Instrumenting your circuit breaker like that could have led us to that discovery faster. But again, this was a novel failure scenario for us at the time. Learning from it, I would say, is the most important thing. You can do all these things. You can read, Google's SRE book or Michael Nygaard's book from back to forth and implement all these things. And then life gets interesting when, despite all of these protections, something still goes sufficiently wrong. And then you have to dig into, okay, why did this circuit breaker not behave as we expected? There's always going to be new ways that your system is going to fail, and that's fine. Have a good retrospective process that is aimed at learning from the problem and not at laying blame or finger pointing, and then also prioritize those requests. Because if I get paged at 3 a.m., that is annoying, but we'll get it under control, and then the next, I sleep in a little, and then we'll go about, putting in a new systems fix to prevent this failure case from happening. What is really annoying, though, is that the week, a month later, when you're on call again, the same thing happens again, and you're paged again at 3 a.m. for the exact same reason. That I don't have any patience for that.
Thank you, Bart. That was packed episode of very, very useful advices, and we have a number of resources we're going to include. One of those is your blog post.
It's called 10 Tips for Building Resilient Payment Systems. But even though I'm coming at it from a payment systems angle, I think a lot of these concepts apply broadly to any kind of application that you're building.
Thank you so much, and good luck.
Thank you, Darko. It was a pleasure being here.
What a great conversation. We hope you enjoyed it and learned something new. Make sure to subscribe to Semaphore Uncut on your podcast player of choice so that you don't miss our new episodes. And stay tuned.